Welcome to this webinar on detecting electrical energy losses using thermal imagers. This is a short webinar on the use of thermal imagers, finding the faults in the electrical equipment like cables, connections, fuses, motors, etc., which can be associated with abnormal electrical energy losses. Presenting is myself, Simon Worrell. I'm the technical sales manager for Fluke, and we're doing this in conjunction with Voltman. At the end of this webinar, it is a CPD certified webinar. We will be sending you out the certificates in the next 1 to 2 working weeks. The webcast today will last about 45 minutes, and then we'll have a session at the end where we can answer questions. If you leave your questions, type them in, and then we'll cover each one individually at the end of the webinar. It is only an initial training, this. It gives you insights as to what can be done with thermal imaging and what the true root causes are behind them. So, as we move forward, what is thermal imaging? Thermal imaging is the measurement remotely of temperatures. Basically, we monitor the amount of infrared energy coming from an object. That is converted into a temperature, and each temperature that is the same gets the same color. See on the right of your screen now. Thermal imaging is very intuitive. Even very non-technical people could take a look at that screen and will be easily able to point out where they think the heat is coming from, the red areas on the picture. It's very effective to inspect, and it covers all sorts of equipment. It can be electrical, electronic, mechanical, even biological. Thermal imagers are now used by vets to monitor muscles and strains within racehorses, for example. So we can do electric equipment, circuits, all the mechanical equipment. We can look at heating and cooling within your building and structure, the envelope itself, and there are many other applications where you can use thermography and thermal imaging. Now, what is thermal imaging? What is infrared energy? Well, infrared energy is part of the electromagnetic spectrum. We're all familiar with the electromagnetic spectrum, or we should be from how we use it. You know, us as humans, we see invisible light. And you can see on screen, we've got a little picture of a digital camera, and this works in the same bandwidth as our eyes do, invisible light. Right next to that, on the electromagnetic spectrum, is the infrared area, and we go from near infrared to long wave infrared. And other areas in this spectrum will be X-rays for your broken bones, microwave for cooking our meals, etc. Even radio waves are all part of the electromagnetic spectrum. For industrial thermography, what we use the long wave infrared between 8 and 14 microns. And this is because at that wavelength, infrared energy is not absorbed by the atmosphere. So we get a true picture with no interference of the object we're looking at. Now, visual light, the light that we see is reflected. Light bounces off the image and reflects into our eyes, and that's how we see it. When we're looking at infrared and radiation, that is actually emitted from the object, and the to the surface of the object is, the more infrared radiation will be generated. So infrared radiation increases with temperature. On screen, you can see the reflected image of a coffee cup. We're all used to seeing that. And now on screen, we've got the same image of that coffee cup, but looking via a thermal camera. And depending on how hot the liquid is inside, depends on how much infrared energy is transmitted. If we was to now put that coffee cup into a microwave, say for 30 seconds to heat it up, what you would see is the infrared energy increases, and we can now see a definite difference between the two images. And we can see that the right-hand image showing red is showing more heat. Some of the benefits of using infrared technology, well, it's non-contact. So operators can use it from a safe environment. If you're looking at objects that are moving, if there is a safety zone for operators that you can't get into, if you've got hot liquids, hot metals at very high voltages, you don't want to be actually touching those voltages. You want to be able to measure your temperatures from a safe distance. When using thermal imaging, as you're going to see in slides to come, they're very sensitive to problem characteristics, and it's very easy to identify some faults just by the picture and how it looks. You can detect problems way before they become more significant. So things in life, electrical, mechanical, even biological, when we start to have problems, first things that happen is we generate excessive temperature. If you take biological, if you think about, athletes and that, they have joint problems where they've been running a lot. We get people with arthritis. They've got two bones rubbing on each other. It creates friction, and that friction will start well before pain is actually sensed by the person, and we can see that. You can scan large areas very, very quickly and then locate down to the problem area itself, zoom in. This is a new installation, and visually it looks a perfect installation. When we put a thermal imager on, what we can actually see is we've got an hot connection. And using a Fluke thermal imager, we can actually take the temperature reading of each pixel on that camera. And for example, we can now see on screen that we've got a maximum temperature of 212 degrees. So it's not very hot. We can blend between thermal and visual, so we can identify clearly visually which is the problem connector. And just as a thought on this one, we're measuring a temperature of 212 degrees. The actual temperature rating of that cable is 160 degrees for 5 minutes. Not only have we found an hot connection, but we've identified that that cable is really damaged. And then we need to look further to see if the actual connector block has been damaged by having excessive heat over a prolonged time. So not only have we been able to identify when we could fix the problem, but we've identified that the actual cable needs replacing. Better to do this at the beginning of a new installation than to find out when production is up and running and you have an overload and a production shutdown. Thermography and thermal imaging is great for seeing before and after repairs. It's estimated that 27%, sometimes 30% of all faults are actually generated by engineers fixing something else, or they've never been properly fixed in the first place. We've seen example line. We've got a hotspot. We'll talk about this in more detail later, but it's a defined temperature, and we're seeing it running at over 190 degrees. Engineer goes out to repair, but using the thermal imager, we can see that even though the repair is much improved and the temperature's dropped by over 100 degrees, we still have a fault there, and that fault will continue to degrade over time, and within 6 months you'll be going back to fix the fault yet again. At least using a thermal image, you can see before and after very, very quickly. And ultimately, us as customers and users of infrared and thermal imaging, we all have customers. They may be internal customers, our own companies and management, or you're selling your services. And for that, when you're using thermal imaging, what you want is good analysis and report software. Because this is what pays you to do the job. When you show this report to your customer, that's what generates the money, not the actual time you've been doing going around and surveying their plant. So you want good analysis software, so you can document reports, you can put cursors on, and then you can formalize it in a good looking report with your company logo on, etc. So that's what you need when you're looking for a thermal imager. But let's drill down into some of the problems. So thermal imaging is all about looking for excessive temperatures. So what causes overheating? Well, in electrical and mechanical systems, it's a component gets overheated because of a number of factors. In our electrical systems, three-phase, it can be by unbalanced load. It can be by harmonic, it can be an increase in resistance of a joint, etc. These are typically what we will refer to as hotspots. Temperature is proportional to power. So an increase in power increases temperature. Power is equal to resistance times your current flow squared. So if you have a resistive connection, either from being a loose connection or over tight or corrosive in your connection, you're getting extra resistance. You've got the same current flow across that resistance, so you've got more power, which results in higher temperatures. And a good rule of thumb is double the power, quadruple the temperature. So if you measure a cable today that has 10 amps flowing through it, and you measure 10 degrees centigrade, if tomorrow you come back and that same cable has got 20 amps through it, well within the limit, you could instantly be recording 40 degrees centigrade. Now, from one day to the next, you've just done two measurements and you've measured 10 degrees, and the second day you've measured 40. It could be you're thinking you've got a big problem, but no, just the load has actually doubled. So bear this in mind when you're doing electrical inspections. Double the load, quadruple the temperature. Now, for a couple of common thermal signatures, and then drill down into the root cause of what's behind them. Thermography is very intuitive when you're looking at things as you are on screen now. These are infrared images of a knife breaker. There we go, which is a mechanical breaker. And then we've got a cable connection, and you can see three phases, and the center phase has got a defined temperature at one point, and then it cools down as it travels along the cable. This is a typical hotspot, and it's either derived from a cable that's too loose, or you've got corrosion and oxidation within the connection, which is creating extra resistance. You don't need to go any further and use any other test tools. The thermal imager has identified what the problem is, de-energize power, undo the connection, clean it up, retighten it, and away you go. What happens when we're using thermography and we get heat, apologies for that, we get heat running down the actual cable, down the length. So it's not a defined hotspot, we've got overheating cables. And this can be for a number of reasons. It can be an unbalance. So we've got one phase at 10 amps, another phase at 10 amps, and one phase at 30 amps. It could be an overload for the ratings of the cables, or it could be harmonics. And what we're going to do now is just to drill down and explain why those three problem areas cause excessive heating. And we're not only just going to look at cabling, for example. If we look at anomalies in motors, a motor is just, it's got lots of windings inside. So if we have problems externally on the cables, we can see them equally within motors. And excessive heat in motors can be inadequate airflow, maintenance of the actual motor, unbalanced voltage or overload, and it can be electric installation failure, or more mechanical things like shaft misalignment or bearing failure. And the reason we're focusing a bit on motors and electromechanical systems is that 60% or more of all our industrial energy that's being produced is being used to drive a motor. If you think about it, just in your office buildings, your manufacturing sites, your air conditioning has motors in it. We're moving cool water to cool and heat our buildings. We've got motors driving production lines. We use motors all the time in industry, and 60% of all energy goes to feed these. And any problem with the motor, whether it be mechanical or electrical, will cause two things: higher vibration and overheating. And both these, we've got tools at Fluke to help you find the actual problem. But for thermography, it's very, very easy. Point it at the cable, at the connector, and then do comparisons as to how hot it really is. So on screen now, you've got the digital image on the left and you've got the thermal image on the right. what we can see here, it looks like on the right-hand cable, we've got a combination of overheating as a hotspot, and then we've got overheating running the length of the cable. The hotspot is easy to determine, but to understand what the root cause of the problem is, you will need complementary equipment. You will need other equipment. And all of you as electricians will carry two-pole testers, maybe clamp meters, maybe digital multimeters. Some of you already have power quality analyzers, and you will use these extra tools to actually determine what the root cause of the problem and causing that heating is. So signature 2, we're going to look at this, and at the moment we're going to address it as unbalance. So we're going to use a thermal imager. We've seen the heat, and now we're going to put a power quality analyzer on, and this will sit on all three phases and do the measurements. If you're using a power quality analyzer, not only does it instantly tell you what you're on, but it will analyze your harmonics and your overload all in one simple measurement. So a power quality analyzer will tell us as a percentage what our unbalance is. And on screen at the moment, we've got a 10% unbalance and a 5.7% unbalance. Those are voltage unbalances. They are way above the maximum allowed for motors. When we're looking at motors, to analyze all sides of your motor, the bearing and the air intake at the rear of the motor. You're looking for non-uniform temperature patterns. So you're looking for excessive heat in areas, as we can see here on the motor. And that would lead you to further use a power quality analyzer to analyze the imbalance, to analyze the overload, and analyze the harmonics. So the starting point is always using a thermal imager. So what is imbalance? On a three-phase system, we want all the voltages to have the same magnitude. So in the UK, it's 230 volts. So we want each phase, L1, 2, and 3, to have the same voltage. We also want them to be separated by 120 degrees. And if the same magnitude with the same phase separation of 120 degrees, that is a perfect balanced system. But what you can have is different amplitudes, and you can have different phase angles between the actual vectors, the phase of L1, 2, and 3. Each of these will give us an unbalance that we can read as a percentage. And just as an example, on motors, voltage unbalance, the maximum that is allowed is 2%. And here we can see a simple screenshot from a Fluke 430 series. It gives us a voltage imbalance of 2.4. So we're outside of the specification for motors there. So we need to drill down into that. Our current unbalance will always be significantly greater than our voltage unbalance. On screen, what we're going to do, we've got two examples of a perfectly balanced system and a perfectly unbalanced system. In this webinar, I'm not going to go through the calculations. They're both there on screen, and as we said you can get obtain a PDF of this presentation and go through it yourselves. But we've got on the left-hand side a perfectly balanced system. Each phase has got 1 ohm and the same current flowing through. And on the right-hand side, we've got a perfectly unbalanced one where we've got all three loads on L1 and nothing on L2 and L3. The key thing I want to point out here is the difference in losses between a perfectly balanced and a perfectly unbalanced system. You can have 6 times greater losses on a perfectly unbalanced system, as this equation down here on both sides is shown. I'll leave you in your own time through the equations yourselves. The second case we're going to look at for an overheating cable is harmonics. Again, you will see these with a power quality analyzer. And usually how we investigate and view harmonics is using them via an FFT and looking at a bar of the harmonics. And we can see all the different harmonic orders up to the 51st harmonic, and we can see the magnitude of them. And by looking at patterns of harmonics will help us understand some of the loads that are connected on our system. Now, why do we suddenly have a problem with harmonics? Well, harmonics are generated by modern nonlinear loads, and these are most loads that have silicon in, so single phase switch mode, rectifiers, bridge rectifiers, three-phase rectifiers, etc. As time has progressed, there's been a big drive to reduce our energy usage. And by putting in more modern, efficient energy equipment, such as new lighting, such as variable speed drives, we've reduced our overall energy usage. But one of these modern electronic devices is create harmonics. We're just going to take a quick example and look at lighting. So on screen at the moment, we've got a thermal image of an incandescent light bulb, which is running at 134 degrees. And we've got the same image of a compact fluorescent, which is running at 39 degrees, approximately 100 degrees less in temperature. So the incandescent light bulb is creating 100 degrees more, which is waste energy. It's energy being created as heat rather than light, and that is a waste energy. But by switching to the new energy efficient LED and compact fluorescents, we save on the kilowatt hours we use. But as we're going to show you in the next couple of slides, they can have a dramatic effect on the harmonics we have present. So an example showing the incandescent light bulb, we have 5 of these connected together for this example, 60-watt bulbs. So we should see a total of 300 watt. On screen, we're actually measuring 291 watts. We have got a little bit of losses. But the voltage waveform, which is a sine bulb, will have a sine wave current derived from it. And when we look at our harmonics, all we have is the 50 hertz, the fundamental harmonic for voltage, and the fundamental harmonic for current, both derived from a sine wave. When we now look at the new energy efficient devices such as compact fluorescent, and we have the same setup, the first thing you will notice is we've got sine wave voltage, but now the current waveform is being distorted. We're drawing bursts of current. And if we look at our harmonics spectrum for voltage, we still have just our 50 hertz fundamental. But if we now go down and look at the harmonics, the current harmonics, you can see it's quite a difference. We've now got a massive range of harmonics going all the way up to the 51st. And if we look at this harmonic here, the third, we've got 75–80% of third harmonic, which can cause other problems as well as heating. But why do we do it? Well, we've reduced 291 watts to 66 watts. So our energy bills will improve. So harmonics in a bit more detail. What is a harmonic? Well, a harmonic is a multiple frequency of the fundamental. And here in the UK and in Europe, our fundamental's 50 hertz. So any harmonics will be multiples of a 50 hertz. So we count them in orders from 1, which is your 50 hertz fundamental, up to your 51st. On screen at the moment, we've got the third harmonic, which is 3 times the fundamental, so it's 150 hertz frequency. Now, if we've got just the fundamental and the third, they're combined to give us a distorted waveform, which you can see on screen now as blue. If we go one step further and add the 7th harmonic, which is 350 hertz, you can see the overall waveform distorts even more. And we go up to the 51st harmonic. So a power quality analyzer will analyze the distorted waveform, and it will break out each of the individual frequencies and give you the magnitudes of them, which we can then use going forward to find the root cause of our problems. Now, harmonics have a sequence all the way from the 1st up to the 51st and beyond. It goes plus, negative 0, repeated all the way through. For positive, the pluses, we have forward rotation. So when they're applied to an example, a motor, they will forward drive the motor. We will have heating of conductors and circuit breakers because we have current flow. For negative sequence harmonics, we have the inverse on rotation. So these will try and drive the motor in reverse. So we have the same heating because we've got current flow in the cables and the connectors, but we will also see problems in motors because any negative sequence harmonics will be trying to drive the motor backwards. A simple example, if we have 10 amps of first harmonic on the motor and we have 1 amp of fifth, not a great example, but just making the numbers nice and simple, we actually have in effect 10 amps driving forward, 1 amp driving backwards. So we only have 9 amps effectively trying to drive the motor forward. So we tweak up the input to the motor, we go to 11 amps and we're stressing the motor. The zero sequence, the nulls, they have no effect forward or reverse for the rotation of motors, but they do have an extra feature, if we can call it that, cause currents to flow in our neutral on 3-star Y systems and star 3-phase systems. The next thing we have to take into account when we're looking, when we have harmonics present in our systems is skin effect. Our wiring in our systems were always designed to operate at 50 hertz, and in years gone past, that's what they did. So when we have our fundamental, the AC current flows to the area of our copper conductors. But when we have harmonics present, what we have is higher frequencies present. We go up to many kilohertz when we're going up to 50th and 51st harmonic. And what happens when you have higher frequencies, they don't flow down the full cross-sectional diameter area of our copper conductors. They actually flow down the outer edges, as I'm going to show you in this short animation. So 50 hertz flows down the entire cross-sectional area, but high frequencies flow down the outer edges. And you've got currents flowing down less copper, so they generate more heat. And another effect of higher harmonic tent is the heat they generate is far, far greater than anything in the fundamental. Let me try and explain this, and I'll try and explain it in layman's terms to make it easier. But 1 amp of harmonic of n order generates heating n squared higher than the same current at fundamental frequency. Let me try and make this a bit. So if I have 1 amp of current flowing at 50 hertz, my fundamental, that would create X amount of heat. If I had 1 amp flowing in my 1 amp of fifth harmonic, that will be n squared. So 5 squared is 25 times the 1 amp. So we have the equivalent heating effect of 1 amp in our fifth as 25 amps in our fundamental. So you can soon see how higher harmonic orders can then generate excessive temperatures that can lead to overheating and shutdowns and problems in your office buildings and manufacturing. So being aware of the higher harmonics is critical. What we have on screen at the moment, we have an infrared thermal image of some cabling, and we can see 2 hot cables. These are our neutral cables, and we're going to look at third harmonic in a bit more detail. Now on the right hand, we've got the picture of an old-fashioned but typical L1, 2 and 3, and you'll notice that the neutral is half the size of the phases. In modern cables, the neutral should be at least the same size as the phases, if not double, because in theory we can get double the amount of current flow in the neutral as we can in the phases. Let me try and explain. We're just going to start with a real live image taken from the computer center. If you just look at the phase currents, 171, 172, 171 amps, very, very well balanced. If you take a look at the neutral, we've got 445 amps, almost 3 times the amount of current flowing. And this is because of the use of the building, a computer center. They've got, well, they have thousands of computers in there. They have printers in there. They have monitors are all LCD monitors now. All these products are powered by single phase switch mode supplies. And single mode switch mode power supplies create a third harmonic. And what you can actually see on screen at the moment, we have L1, 2, and 3, and the fundamental in blue, in green, and in purple. If on a perfectly balanced system, 120 degrees apart, they should all fully cancel out at the neutral point, the starts here. So you will have no current neutral from your fundamental. But on screen, we've got third harmonic. If you draw a line between all three phases, at any point along that third harmonic waveform, they're always in phase. So they do not cancel out at the neutral. What they actually do is add together and flow in the neutral. So using a thermal imager, if you spot hot temperatures in your neutral, the first thing to actually go on is look for unbalance, which can cause neutral currents, but also for third harmonics or tripling thereof. So third, ninth, 15th. We tend to ignore the even harmonics because they tend to indicate we've got DC present in our system, which is another problem. So third harmonic and triplings of that all add up, are always in phase with each other, add up and cause current to flow in our neutral. And this brings us back to an important thing because there's lots of choice for your power quality analyzers that are out on the market. If you are going for one, make sure you go for a unit that measures the neutral current and doesn't calculate. There are lots of low-cost analyzers in the market that will calculate the neutral current and what you've got present. When we're looking at motors, essentially I'm repeating everything I've said because a motor, three-phase motor, for example, 3 sets of windings wound around a toroid within the motor. Motors drive a lot of our business. You know, if a motor stops, your production line stops. Your air conditioning. Winter, you can be in a building that's very, very cold. In summer, the odd few weeks we get of a scorching summer, you can be in a building that's unbearably hot. And there are criteria for maximum, minimum temperatures. But anything that is creating excessive heat is wasting energy. So you're paying for electrical energy to be converted into heat energy and just wasted. Using the thermal imager on screen, we can see we've got 2 motors doing similar things. We've got the normal one running at under 40 degrees. We've got the hot motor at over 85 degrees. This will do a number of things. Hot motors will reduce the efficiency and the effectiveness of the insulation. And we're going to come on to that later. So effectively reducing the lifetime of the motor. So it costs you more, not just in running costs, but in replacing motors. So using thermal imaging and do it from all sides of the motor because you can get defined hot spots on the motor where insulation's broken down. And you can blend it with the visual of we've got on the right hand side of the screen so you can make easy identification of motors. When motors are hot, you can also use vibration testing. This is another way of finding out if you've got problems. You know, you can have problems with your bearings, and just jumping back into harmonics, harmonics can cause bearings to degrade. High frequency harmonics in motors tend to short circuit the bearings, so they arc across and cause small pits in the bearing that over time get worse with the mechanical load the bearing's under, and the bearing breaks down well before the end of its nominal useful life. So you can use vibration meters as well as thermal imaging. And again, skin effect within motors has the same effect as within the cables. If you've got high harmonics, then you've got high surface temperature of the cables, which creates the motor to run hotter than it should. Also, when we're looking at how sequence is very important, as we've said earlier in motors. If we look at the fifth harmonic negative sequence, and fifth harmonics can be generated by 3-phase rectification. They will generate fifth and seventh, 11th and 13th harmonic. So modern devices, variable speed drives, make our motors more responsive and more energy efficient, can cause us other problems for the motor. So if we have a lot of fifth harmonic, this will cause inverted rotation, so we'll put extra stress and cause extra heating on our motors. And all your motors will have a nameplate on them. It will tell you the kilowatt or the horsepower of the motor. It will tell you the RPM. But another key factor on the nameplate will be the maximum temperature. If you exceed the maximum temperature by just 10 degrees, the insulation life inside the motor will be reduced by 50%. 20 degrees, 75%. 30 degrees, 88% roughly. And if you've got a motor that's overheating by 30 degrees, whether that be by bad maintenance, you're not keeping the air vents clean, by mechanical problems or electrical problems, harmonics overload, etc., then you might as well have a stock of motors sat in your storeroom because you're going to be replacing them out. And even a motor that you spend £10,000 on and you expect to last 10 years, if you're running it 10 degrees hotter, installation life will be reduced by 50%. Motor fails 50% earlier, so it fails in 5 years. So you have to buy another one. And without correcting for the root cause, that one fails in 5 years. So you've doubled your initial investment. And also, because the motor broke when you wasn't expecting it, the actual cost of repairing that and buying a motor at peak cost because you need it immediately, all adds to the overall cost. So how can we measure energy waste? Well, we can see energy waste just by overheating. Anything where electrical energy or mechanical energy is converted to waste, that is waste energy. So we're paying for it and then we're just using it to heat our homes and buildings. The number of being across where people have replaced halogen lighting for LED lighting and then complain that their buildings are now not warm. Well, they've been using inefficient halogen bulbs to effectively compensate for their heating systems. So they've been paying cost of lighting, also using it to heat, and it's a very, very inefficient way of heating your buildings. So how do we actually measure it? Well, we can do simple comparisons to see how much heat we're losing, but once we know losing heat, we can actually use power quality. And Fluke have got some patented models that actually can measure and analyze and cost out where the losses are. This will be on our 430. It is patented technology, and what you can see on screen at the moment, it will measure our effective loss, which is our I squared R in our cables. This is very hard to correct and compensate for because most buildings are pre-wired, and to strip buildings out once they've been built, to rewire, put bigger cables in, etc., is very expensive. But we can analyze our react power. We can look at our total losses as watts and kilowatts, our losses in this case is dollars, and then annualize that up. We can look at our imbalance, our distortion, and our neutral currents. So we can look at what the maximum cost is over a year, and then we can address that problem first to actually save energy. I've actually gone through this a bit faster. I normally allow 45 minutes, so I hope you have kept up, but let's go through some conclusions. When doing infrared surveys of mechanical and electrical equipment, it's very easy to spot and to identify certain problems. If we look at the left-hand image, we've got our cabling, where it's just the neutral cables that are overheating. Unbalanced or more likely third harmonic caused by modern single-phase rectification. On the middle image and the right-hand image, we've got overheating motors. That can be from a number of causes. The overheating could be simply a terminal connection problem. So we've got heating at our terminals, it's been transferred into the motor. But more likely, it will be from a breakdown in the insulation resistance or the insulation of our cabling, generates heat before it actually fails. And this is caused by harmonics creating extra heat, which reduces insulation life, unbalance or overload, both mechanical and electrical overload. So using thermography is very easy to not only find certain faults, but to identify where we've got energy waste. And you will need complementary equipment. There's no electrical engineers out there that just go out with a two-pole tester or a voltage detector. Most will have access to digital multimeters. Most will have access to clamp meters. And if you're in the industrial world, you've probably got access to thermal imagers, energy loggers. So you will need complementary equipment. Finding a hotspot, you don't, but overheating cable, overheating motor, you need other tools to identify the root cause of the problem. Now, what is your next step out there? Well, obviously, working for Fluke, I think your next step should be to go and invest and buy yourselves a Fluke thermal imager. But first things first, download the free analysis and report writing software. When you download it, it is free. Well, nothing's free, but the software and hardware are combined as one. So you can freely download SmartView software from Fluke's website. You will get some images, so you get the opportunity to play, to put markers, to put cursors on the image, to write notes, and then to generate a report. Simple, go to fluke.co.uk, go on to support and go to software downloads, and we will provide you information. We'll be contacting you in the days following this webinar. You can contact us directly, you can go through Voltimum, but we will provide your CPD certificate, so you will get contact information later. There are other elements. Via Fluke, we do principles of thermography. It's actually called Introduction to Thermography Principles. It's an education book. It's in electronic format, so we can email you this out. And again, this is free. If you want information on power quality, because obviously power quality and thermography go hand in hand, there are more in-depth, paid for power quality trainings on the Fluke website. It's a paid for course. It lasts 8 modules and it's a web course which you do in your own time. But if you want to have a look at it, part 1 is free. So you can see the quality of what you're going to be paying for. It's about £160. But go on, register on there and look at part 1 for free. On screen at the moment, we've got email address helen.berry@fluke.com. Helen will be the one sending the information out, but we will be contacting you shortly with Voltman to send out your CPD certificates. And at that point, you'll have the opportunity to give us some of your details and put requests in for the slideshow and maybe the introduction to thermography booklets. That is the end of this short webinar. I thank you for your time. What we're going to do now, we're going to over and review any questions, and I'll take the questions one at a time and do my very best to answer them. So, okay, Stuart's asked a question. Hi, Simon. On the connector blocks slide with the 212 degrees, what emissivity would you use for this? Okay, emissivity is a setting that you can select on the thermal images themselves, or with the Fluke software, you can actually change it later on. When I do a more in-depth thermal imaging seminar and I'm doing surveys, I try and leave my emissivity set roughly between about 0.92 and about 0.95. And I take my measurements on the actual plastic or the insulation material, whatever type of PVC it is. When you're doing measurements on metals, shiny metals reflect infrared energy, so they can make the errors very great indeed. So when I'm doing measurements on metals, I'm doing a comparative measurement. So I'm doing it between one point and a similar point. But for that slide alone, we took the measurement from the plastic or the insulation on the cable. And when I do my surveys, I leave my camera set usually 0.9 to 0.95. I hope that helps. Okay, John, thank you for your feedback. And while you're all still listening, John's just given me some positive feedback, which is great. Everyone likes a pat on the back. But if you do have any constructive criticisms, both Fluke and Voltman, we're here to improve. So if there is any advice you've got, any things you think we can change, can contact us both at Fluke or Voltman. We're always looking to improve. If we deliver a good presentation, it means, you may be willing to look at our products in the future. And if any of you want to see any Fluke products, thermal imaging, power and energy analyzers, etc., please contact us at Fluke. We do not sell direct, but we will come out on site and do demonstrations for you. Stuart's just asked another question. Is there a set standard for reports, an IEC standard? No, there is not. I know there are various groups looking at thermography going forward. We've already seen some changes with 18th edition where there's no requirements, but there's recommendations, and with various trade bodies, they're introducing thermography into 18th edition at the moment. When you get the Fluke software, you get a number of templates to actually generate reports, 5 in fact, and you can modify them for your own needs as well. Thank you, Liam, for your comments. Oh, sorry, Elamin? I work for an electrical company. We start working on thermal field now. We set up a report to pass DBS below 60 degrees. Do you agree? Okay. There is no wrong and right about this. There are some guidelines. We do have the old VDE guideline that the Germans use, and we have the NETA guidelines that the Americans use. Now, they're both very, very similar, and they both say if you've got similar loads, if you've got similar components working on similar loads, you should expect less than a 15-degree difference between those components. You also need to make sure that the DB, the distribution board you're working on, that is no more than 30 degrees above the ambient. I don't know where you're working, Elaine, whether in the UK or you could be in the Middle East, etc. But for example, in the UK and London, we have some electrical installations that are effectively on the outside of buildings. Well, we can do a measurement in the middle of winter when the ambient temperature is 0 and a connector could be at 30 degrees. We could say, yeah, that's great, it's within the tolerances. But on that one day in summer when the ambient temperature is at 35 degrees, that connects sat at 65. So it could then be outside the specification. If you're working in a very hot country and the ambient on the outer box of your DB is running at 30, 35, then your actual elevation is only 30 degrees above. But 60 degrees, I tend to start to get worried above 70 degrees. And, I've been into many DBs where they're running in excess of 100 degrees. I hope, Elamin, that has answered your question. Oh, you do work in the UK. Well, 60 degrees, I would want to monitor and keep monitoring that. At 60 degrees, depending on the load of it and other issues that go in, I will be monitoring that every 3 months. The only source, Stuart, for all these figures is the VDE spec from Germany and the net spec from America. The Americans use that. In Europe, we've got IEC, and there are no fixed specifications. When we send you out your CPD certificate, Stuart, you'll have our details. Send your details in to us. We'll be doing this over the next few days, probably running into next week. We'll start communicating with you. We'll be able to send you some extra information. Okay, at the moment, I think we've answered all questions. We will stay online for another few minutes. But once again, from me at Fluke and Voltzman, thank you very much for your time.